This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to this discussion on a fascinating paper exploring the intersection of large language models, LLMs, robotics, and formal verification. The authors propose a framework for ensuring the safe operation of robots controlled by LLMs, even in unpredictable environments. What are the core safety challenges posed by using LLMs to control robots, and how does this paper address them?
The primary challenge stems from the probabilistic nature of LLMs. Unlike traditional rule-based controllers, LLMs produce outputs based on probabilistic reasoning, introducing uncertainties difficult to model or verify. This is particularly problematic in safety-critical applications. Minor adversarial modifications to input prompts or sensory data can significantly degrade performance, leading to unsafe robot behavior. This paper tackles this by employing data-driven reachability analysis, a formal verification technique that provides guarantees that all possible robot trajectories remain within safe operational limits. It avoids the need for precise, often inaccurate, analytical models of the robot and its environment.
Reachability analysis is a powerful tool. How does the data-driven approach differ from traditional model-based methods, and what are its advantages in this context?
Traditional model-based reachability analysis relies on precise analytical models of the system. These models are often difficult, if not impossible, to obtain for real-world robotic systems, and they may not fully capture the complexities of real-world dynamics and environmental uncertainties. The data-driven approach, in contrast, leverages historical data to construct reachable sets, effectively bypassing the need for an explicit analytical model. This makes it more robust to model inaccuracies and uncertainties. The paper uses zonotopes and constrained zonotopes for efficient representation and computation of reachable sets.
The paper mentions the use of zonotopes and constrained zonotopes. Could you elaborate on why these specific set representations were chosen and what advantages they offer for reachability analysis?
Zonotopes and constrained zonotopes are chosen for their computational efficiency, particularly in higher dimensional state spaces. They allow for efficient computation of the Minkowski sum, a crucial operation in reachability analysis. Constrained zonotopes are a generalization of zonotopes, allowing for the representation of more complex convex polytopes by incorporating constraints on the generated vectors. This allowed for a more accurate representation of the reachable set while maintaining computational tractability.
The framework incorporates a safety layer that refines LLM-generated plans. Can you detail the process of adjusting unsafe actions and the role of gradient descent in this process?
The safety layer checks if the reachable sets generated from the LLM's plan intersect with any obstacles. If an intersection is detected, the layer uses gradient descent to adjust the plan, iteratively modifying the control actions to avoid collisions. The gradient is computed using a chain rule recursion, considering the dependence of the reachable set center on the control actions. The adjusted actions are then projected onto the feasible control set to ensure they remain physically realizable. If the adjustment process fails to converge within a specified time, a fail-safe maneuver.com breaking is executed.
The paper presents experimental results with a Turtlebot 3 and a jet racer. What were the key findings from these case studies, and how well did the framework perform in practice?
The experiments demonstrated the effectiveness of the framework in ensuring safe operation of both robots in various environments with different obstacle configurations. The data-driven reachability analysis successfully prevented collisions, even with noisy sensor data and the inherent uncertainties of LLM-generated plans. The results highlight the scalability and adaptability of the approach, showing its potential for real-world deployment. The paper also compares the proposed method with an alternative approach, AISS, highlighting the advantages of the formal safety guarantees provided by the reachability-based method.
The paper mentions limitations and future work. What are some of the key areas for improvement or extension of this framework?
One limitation is the computational cost of reachability analysis, which can increase with the complexity of the environment and the planning horizon. Future work could focus on developing more efficient algorithms for reachability analysis or exploring techniques to reduce the computational burden. Another area is integrating feedback mechanisms into the LLM control loop to improve the quality of LLM-generated plans and reduce the need for extensive adjustments by the safety layer. This could involve developing a stateful interaction model or fine-tuning LLMs with safety-aware training data.
The paper emphasizes the importance of a fail-safe maneuver. How crucial is this element to the overall safety and robustness of the system, and what are some considerations in designing an effective fail-safe?
The fail-safe maneuver is absolutely crucial. It acts as a last resort, ensuring safety even if the LLM-generated plan or the reachability analysis fails to prevent a collision. The design of an effective fail-safe depends on the specific robot and its capabilities. It should be simple, reliable, and guaranteed to bring the robot to a safe state within a reasonable time frame. The paper assumes the robot can brake to a complete stop within a known number of time steps, but other fail-safe strategies could be employed depending on the application.
The paper highlights the use of offline data for training the reachability analysis, how much data is needed, and what are the considerations for data collection and quality.
The amount of data required depends on the complexity of the robot's dynamics and the environment. Sufficient data is needed to accurately estimate the Lipschitz constant and the data covering radius, which are crucial for the accuracy of the reachability analysis. The data should be representative of the operating conditions and should include a range of possible inputs and disturbances. The quality of the data is also critical. Noisy or inaccurate data can lead to overly conservative or inaccurate reachable sets. The paper suggests collecting 600-step noisy input/output data offline in an empty environment as a starting point.
The paper uses a specific LLM, GPT-4o. How much does the choice of LLM impact the performance and safety of the overall system? Could other LLMs be used, and what factors should be considered when selecting an LLM for this application?
The choice of LLM can significantly impact performance and safety. Different LLMs have different capabilities in terms of language understanding, reasoning, and generating coherent plans. The selected LLM should be capable of understanding the robot's state, the environment, and the task instructions provided in the prompt. It should also be able to generate plans that are both feasible and safe. While the paper uses GPT-4o, other LLMs could potentially be used, but careful evaluation and testing would be necessary to ensure their suitability for this application. Factors to consider include the LLM's accuracy, robustness to noisy inputs, and computational cost.
The paper mentions the use of a temperature parameter in the LLM. What is the role of this parameter, and how does it affect the balance between exploration and exploitation in plan generation?
A temperature parameter controls the randomness of the LLM's output. A lower temperature leads to more deterministic and less creative outputs, favoring exploitation of known good strategies. A higher temperature increases randomness, encouraging exploration of new possibilities. In the context of robot control, a lower temperature might be preferred for safety-critical tasks, while a higher temperature could be beneficial for exploration in less critical situations. The paper uses a temperature of 0.1, suggesting a preference for more deterministic plans in their experiments.
The paper focuses on single-agent navigation. How could this framework be extended to handle multi-agent scenarios or dynamic environments where obstacles are moving?
Extending the framework to multi-agent scenarios or dynamic environments would require incorporating predictions of other agents' motion and the evolution of obstacles. This could involve using techniques like motion prediction models or incorporating uncertainty in the reachability analysis to account for the unpredictable behavior of other agents or moving obstacles. The paper mentions that reachability-based frameworks for handling dynamic environments and other agents' motion could be used to extend the applicability of their work.
The paper mentions the use of LiDAR data in the prompts. How important is sensor data integration, and what are the implications of sensor noise or limitations on the safety and performance of the system?
Sensor data integration is crucial for accurate state estimation and safe navigation. The LiDAR data provides information about the robot's surroundings, allowing the LLM to generate more informed plans. However, sensor noise and limitations can affect the accuracy of the reachable sets and potentially lead to unsafe behavior. The framework needs to be robust to sensor noise and uncertainties. Techniques like sensor fusion or robust state estimation could be employed to mitigate the impact of sensor noise. The paper assumes perfect sensing, but in reality, sensing limitations would need to be accounted for, potentially by incorporating a minimum detection distance to ensure safety.
The paper concludes by suggesting future work on integrating feedback mechanisms. How could feedback from the reachability analysis be incorporated into the LLM's plan generation process to improve performance and reduce the need for manual adjustments?
Integrating feedback would allow the LLM to learn from the results of the reachability analysis, improving its ability to generate safe and efficient plans. This could involve developing a stateful interaction model where the LLM maintains a memory of past plans and their corresponding reachable sets. Alternatively, the LLM could be fine-tuned with safety-aware training data, where the training data includes examples of safe and unsafe plans and their consequences. This would allow the LLM to learn to generate safer plans from the outset, reducing the reliance on the safety layer for post-hoc adjustments.
The paper uses a discrete time model for the robot dynamics. What are the implications of this choice, and how might a continuous time model affect the reachability analysis and the overall framework?
Using a discrete time model simplifies the reachability analysis as it reduces the problem to a sequence of discrete steps. However, it can also introduce discretization errors, which can affect the accuracy of the reachable sets. A continuous time model would provide a more accurate representation of the robot's dynamics, but it would also increase the complexity of the reachability analysis. Techniques like hybrid systems modeling or approximate methods for continuous time reachability analysis could be employed to address this.
The paper focuses on navigation tasks. How adaptable is this framework to other robotic tasks such as manipulation or complex assembly operations?
The core principles of the framework using LLMs for high-level planning and data-driven reachability analysis for safety verification are applicable to a wide range of robotic tasks beyond navigation. However, the specific implementation details, such as the definition of the state space, the control inputs, and the safety constraints, would need to be adapted to the specific task. For manipulation tasks, the state space might include the robot's joint angles and the position and orientation of manipulated objects. For assembly operations, the safety constraints might involve avoiding collisions between the robot and the parts being assembled.
The paper assumes static obstacles. How would the complexity of the reachability analysis change if the obstacles were dynamic and their future positions needed to be predicted?
Incorporating dynamic obstacles significantly increases the complexity of the reachability analysis. It would require predicting the future positions of the obstacles, which introduces uncertainty. The reachable sets would need to account for this uncertainty, potentially leading to more conservative approximations. Techniques like probabilistic motion prediction models could be used to estimate the future positions of dynamic obstacles, and these predictions could be incorporated into the reachability analysis. The uncertainty in the obstacle predictions would need to be propagated through the reachability analysis to ensure safety.
The paper mentions the Lipschitz continuity of the system dynamics. How crucial is this assumption for the data-driven reachability analysis, and what are the implications if this assumption does not hold?
The Lipschitz continuity assumption is crucial for the data-driven reachability analysis, as it guarantees the existence of a Lipschitz constant that bounds the growth of the reachable set. This allows for the construction of a finite over-approximation of the reachable set. If the Lipschitz continuity assumption does not hold, the reachable set might grow unbounded, making it impossible to construct a finite over-approximation. In such cases, alternative techniques for reachability analysis, such as those based on neural networks or other approximation methods, might be necessary.
The paper uses a receding horizon approach. What are the advantages and disadvantages of this approach compared to other planning methods such as global planning or hierarchical planning?
The receding horizon approach offers several advantages, including its ability to handle dynamic environments and uncertainties. By repeatedly replanning over a finite horizon, it can adapt to changes in the environment and correct for errors in the previous plans. However, it can also be computationally expensive, especially for long horizons. Global planning methods, on the other hand, can be more computationally efficient but may not be able to handle dynamic environments as effectively. Hierarchical planning methods can decompose complex tasks into simpler subtasks, but they may require careful design and may not be suitable for all types of tasks. The choice of planning method depends on the specific application and the trade-off between computational cost and adaptability.
The paper focuses on ensuring safety. How does the framework balance safety with performance and efficiency? Are there trade-offs between these aspects?
There is an inherent trade-off between safety, performance, and efficiency. Ensuring high safety guarantees often requires more conservative approximations of the reachable sets, which can lead to reduced performance and increased computational cost. The choice of parameters, such as the planning horizon and the accuracy of the reachable set approximation, affects this balance. The framework aims to find a balance between these aspects by using efficient set representations and algorithms for reachability analysis, while still providing strong safety guarantees. The experimental results demonstrate that the framework can achieve a reasonable balance between safety and performance in the considered case studies.
This has been a very insightful discussion on the paper's contributions and implications. Thank you.